All right, when we're wiring up our op amp, what we need is what we call a dual-ended power supply. And so what we have are these two power supplies wired up in series aiding or series opposing?
Aiding.
Series aiding. So we're going to have two power supplies that need to power up this op amp. And then we have a reference point that's in between there. And what this is going to do is it's going to give us on pin 7, that's going to give us a plus 15 volts. And on pin 4, it's going to give us a negative 15 volts. So we have this dual-ended power supply using two physical power supplies. If we don't have this is the extra credit lab, but it's very costly. Each one of these power supplies are going to be several $100s. Plus, we might not want to use up both of our power supplies just to power up an op amp. So what we do is we can use our one power supply, and then we can go into our Zener regulator. And this will be our load going across them. So if I have my 30 volts, well, we need to be a little bit more. We'll bump it up a little bit, make it track. 40 volts. So we might set we'll set up our power supply up to 40 volts. We're going to have two 15-volt Zeners. So each one of these Zeners, again, remember the diodes always are going to take their voltages first. So each one of these Zeners are going to take 15 volts. And then we're going to have, and again, just like anytime we're working with solid-state devices, we have to have some current-limiting resistors. Otherwise, those diodes are going to try taking all the current they can. End up either blowing our fuse on our circuit or burning out our other power supply. So we're going to have our two current-limiting resistors here. And each one of those are going to drop our 5 volts. And that's going to limit our current going through there. So if I go around in a complete circle there, I'm going to get a 5 volt drop here, 15 volts here, so I'm at 20, plus another 15 volts for this Zener, that's going to be at 35, and then another 5 volts across RS, and then back into my power supply. Now if I'm using a power supply, I really actually I can get by with just one current limiting resistor, but if I'm making my own power supply and using a bridge rectifier with a transformer and stuff like that, then because of the way the current flows, we typically will have our two current limiting resistors in there. So then I take my current path and I drop my current path in polarity. Here's my negative positive. I'm going to come through. Got negative positive coming up. My current is going to come up. It's going to split. Some of it's going to go up to the Zener. Some of it's going to go up through my load. Those two currents are going to combine, and then I got my total current going through my RS again. So I got all my current coming through. All my current's going to go through my first current limiting resistor. My current's going to split, depending on how big of a load I have. Some of my current's going to go through my load. The remainder amount of current's going to go through my zener. Those two currents are going to remain constant until they come up to the next current node. Then those two currents are going to combine, and that's going to give me my total current going across my next current limiting resistor and then back into my power supply. So then, if I'm looking at my voltage drops across, so here's test point A, here's going to be my ground, and then my test point B. Referencing it to ground, what I'm going to get for voltage at test point A, if I bring my red lead down to my black lead, I know that I'm going to be coming down. My first sign I'm going to see is positive because I'm in a reverse biasing on my zener. I'm going to have a positive 15 volts going to ground. So test point A is going to give me a positive, give me my positive 15 volts. Then if I look at test point B, again, referencing my reference point, bring my red lead up to my black lead, come around. First sign I see is negative. The zener is going to drop at 15 volts, and then that's going to give me my negative 15 volts. So then in turn so what I could do then is I could just go ahead with one single power supply. I could get rid of these. Bring test point A over to here, that'll give me my positive 15 volts. Come over to test point B, come over to here, and that'll give me my negative 15 volts going to my op amp. And then I would go ahead and I would just tie my two grounds together. So I can make myself a dual-ended power supply with just one power supply, and it's also going to be regulated, so it's always going to be regulated going into my op amp. So if I put a load on there, it's not changing my voltage. So why we need to have that dual-ended power supply is because my output, because if I'm powering this thing up to plus to minus 15 volts, I have a 30 volt voltage potential, but referencing it to ground, I'm going to get a positive 15 or a negative 15. So the output of my op amp then can either go to, and because of the internal circuitry up here, I'm going to get a voltage drop across here because it is solid-state devices in there, so most of those are going to be dropping, 0.7 volts. Every time they go through a PN junction, it's going to drop 0.7 volts and stuff, just like we did with our BJTs and our zeners and our diodes and stuff like that. So there's going to be some voltage drops in there. So the output can either go to 90% of our source. So the output is always going to be equal to 90% of my source. So if I have a plus 15 volts, positive 15 volts on my pin 7, then my maximum positive voltage would be 90% of 15 volts, which would give me what?
13.5 volts.
Yeah, 13.5 volts. I can go up to a positive 13.5 volts. Then it also can will swing down so that it gives me a negative 15 volts at 90%, and that'll give me my negative 13.5 volts. So my output can swing either to a positive 13.5 volts or a negative 13.5 volts, depending on what my input signals are, my differential signals are. So let's take a look at our differential inputs then. So what we're looking at is we need to determine, first of all, what is the gain of my op amp? And this is what I was looking on the data sheet. Normally they give you what their gain is with an open loop comparator. But our gain can be anywhere from 100,000 to 200,000. Okay, so very large amounts to gain. Okay. So in an open loop comparator, we're going to have something around 100,000 to 200,000. An ideal op amp would have it in the millions, but the practical purposes is that on an open loop comparator, we're going to be at 100,000 to 200,000 gain, which is going to still be quite a bit. We'll we'll see that here. So our first thing that we want to do is when we're analyzing our comparator then is we want to, determine which of these two signals is more positive. So is V1 more positive than V2 or is V2 more positive than V1? Which one is more positive, V1 or V2?
V1.
V1. So V1, so we just kind of tell it we're going to point to V1, which one's the more positive one, and we look at what the sign is. So it's going to be our non-inverting signal. It's going to be our non-inverting input signal is the one that's the most positive. So at that point then, we already know that my output's going to go positive. So what we need to look at then is that we're going to look at, this one's more positive, and it's going to take a look and figure out what the difference is between them. So what is my voltage difference between these two signals?
2 volts.
So what's the difference between 0 volts and plus 1 volt?
1.
1 volt. So my difference of this first one then is going to be 1 volt difference. And it's going to be on our non-inverting pin. And if I took, so it's going to take the difference, it's going to be 1 volt, it's going to take the difference of those two signals, and then it's going to multiply it by the gain, which is 100,000 and 200,000. So I take 1 volt and times it by 100,000, I would get 100,000 volts, is what this op amp is going to try driving that at. Well, we know that my op amp can't go any higher than our VCC at 90% of it, so we know that my op amp can't go any higher than 13.5 volts. So what's going to happen is that this thing is just going to max out, and that first one then is going to just go up, and the output is going to go to 90% of our VCC at a positive 13.5 volts. So if I put 0 volts on this one, put plus 1 volts on this one, it's going to take the difference of those two, take the 1 volt, multiply it by its gain, which is going to exceed the 90% of our VCC, and then it's going to go into saturation, and it's going to bring it up to 13.5 volts.
So V1 and V2 are separate power supplies, right?
Yes, those can be two separate, yep, those are two separate signals. Yep, two separate power supplies. Now in this particular one, since V2 is actually plus or minus 0 volts, it's the same as my ground. Yep. Doesn't necessarily have to be exactly tied into ground, and that's what we call like our virtual ground. But if it's plus or minus 0 volts, if I went from here and I went to whatever this signal is, the difference, I'm going to get 0 volts. Yep. But it doesn't necessarily mean that it's physically tied to this ground. It's just at 0 volts. It has the same voltage potential as our reference point, so that's what we call our virtual ground. All right, so let's take a look at our next one here.